Hi everyone, I'm Cheng Chi from Sunfo Technologies. I will give the session bridging the gap between research and practice in intelligently bypassing WAF. First, let me briefly introduce myself to you. I'm a technical expert at Sunfo Technologies, responsible for exploring the application of AI technology in network security. My research interests include AI security and data-driven security, and I have published at several top journals and conferences, such as Using Security, Army, IPS, CPR, and AAA. My homepage is also shown on the slide. I will start my session from the following parts. First, I will start with several representative works to introduce the latest research progress of AI-enabled intelligent cyber attacks. Then I will point out the two key issues that this research work will face when we want to implement them in practice. Then I will describe what our research is trying to achieve and what the audience can gain from my session. In the fourth part, I will describe how we try to solve the two problems mentioned above. Next, I will introduce the core algorithm in our scheme. Finally, I will show the experimental results we have achieved so far. First, let me introduce some related works in the field of AI-enabled intelligent cyber attacks. Research work from Endgame both inviting machine learning malware detection at Red Hat USA 2017 use reinforcement learning algorithm to fight against AI detection energy in the detection of static window PE files. The setting of the environment is similar to ours, consisting of an AI-based static classifier, and the score of the classifier is directly used as a reward feedback. Agent also takes this as input and outputs selected actions. The feature used here has 2,350 dimensions, including file information, header, and section features. Mutation methods are also classified, which can be divided into three categories: create, add, and modify. After 15 hours of training and 100,000 rounds of iterations, a pass successful rate of 28.5% can be achieved. The team of Professor Chuming Wu from Zhejiang University also published a research work, AutoSphere, towards automatically bypassing and inspecting web application firewalls like Asia this year. They use the model curl tree search algorithm to conduct research on circle injection attacks. Mutation techniques based on syntax tree is used. The key process in their scheme has four parts. First of all, the payload must be parceled into a tree structure. To achieve parsing, the payload is first divided into three parts: the left and the right borders and the circle injected into the query. And then the query part is parceled into a tree structure. The second step is to mutate the payload through the preset mutation method. The core algorithm guiding the mutation search is the Monte Carlo tree search algorithm, and the search process is divided into four steps: selections, expansion, simulation, and backpropagation. Finally, you need to reverse to build this tree into a payload. In addition to reinforcement learning algorithm, there is another type of representative methods that use a genetic algorithm. Take the work of Senyun University in South Korea as an example. They first mutate the original payloads through multiple random selections of actions, and the generated mutate payloads will be scored by the detection energies, and the top K payloads will be selected in descending order according to the score, and then a certain amount will be randomly selected from the variation history payload list and the original payload list, and then repeat the above steps for this payload until the maximum number of mutations is reached. In terms of environment construction, in addition to directly using WAF, some researchers also use machine learning models to simulate. In WAF research work of University of Genoa, they first constructed a dataset of malicious payload and normal traffic, trained some machine learning binary classification models through this dataset, and extract them through some circle feature extractors. The obtained features are then sent to SVM, graph network, and RN for training. Use this model to score the mutated payload until the payload score is lower than the set threshold or reach the maximum number of mutations to end the current payload mutation process. Next, I will point out two key issues that these research works will face when we want to implement them in practice. First, previous research work focused more on sample generation. No matter reinforcement learning, genetic algorithm, or other AI-enabled method, they all rely on huge number of attempts to generate enough data to train the model. We all know that AI algorithm rely on big data. Larger the amount of data, the better the effect of the trained model. However, current commercial WAFs have the blocking IP function. If too many attack attempts are made, the IP will be blocked. So we need to minimize the number of attack attempts in the actual application environment and strive to achieve the effect of one hit no all. Another key issue is that traditional web fuzz methods change the semantic of the payload. For example, when we mutate secure injection payload, we often insert some special characters into the payload, which may cause change in the semantic of the payload. Mutated payload may pass the WAF, but cannot execute the attack directly on the servers. Therefore, we should try our best to ensure the semantic of the payload remain unchanged during the mutation process. Then I will describe what our research is trying to achieve and what the audience can gain from my sessions. Here I give a real and specific example to show the effect of our subject. I take secure injection as an example. Here we have one original payload, one union select one version. It is simplest payload to query the version information of the database. I'm sure that every WAF would block this payload, and we also have three atomic bypass action. Number one, adding all false logic to the payload. Number two, replace all to double vertical bar. Number 3, replace equal to like. These 3 actions are the most basic bypass actions. Hard to use them to bypass commercial WAF. I will show you how our scheme use the combination of these 3 actions to bypass commercial WAF. The progress is fully completed by reinforcement learning agent, and it is shown in the slide. First, true or false logic are added. The payload is mutated to 1 or 8916 equal 8917 or 7641 equal 7642 using select one version. Then 2 or are replaced to double vertical bar. Finally, 2 equals are replaced to like. So far, this payload can already bypass several commercial WAFs. Let me briefly introduce how it works. As the red and blue line show in the slide, it uses a syntax difference between MyCircle and Oracle. The semantic of this payload in MyCircle are the same as the original payload. However, double vertical bars are concatenation operators in Oracle. Connecting two strings, its processing priority is higher than like. Therefore, during the parsing process, when it's found that the two sides between the double vertical bars are not strings, WAF will think that it does not conform to the Oracle syntax, and will let him go. Reinforcement learning agent in our scheme learn to simply combine atomic bypass actions to discover complex bypass pattern. This is the most valuable contribution of our work. Here we summarize 3 main takeaways. Our research is helpful to security researchers, WAF vendors, and penetration test engineers. Security researchers can use some basic mutation operations to obtain some complex bypass patterns, which is very helpful to the research and the utilization of vulnerabilities. WAF vendors can use our algorithm framework to fight against their own WAF, search for bypass points and fix them. They can achieve the promotion effect of attack and defense. Penetration test engineer can directly use our model for penetration testing, which can automatically bypass the specific WAFs. Next, I will describe how we try to solve the 2 problems mentioned above. We first review the workflow of all human bypass WAF. When human want to bypass WAF, we will first try with 1 or 2 original payloads. If it is blocked, we will mutate the dangerous function or variables in the payload, and then use the mutated payload to try until it can bypass successfully. We find that the whole process is constantly interacting with the environment and learning with accumulated experience. It is very similar to the process of reinforcement learning. So we designed the whole scheme based on reinforcement learning. In our scheme, we treat offense and defense confrontation as a game for reinforcement learning agent to play. We design a bypass action library that is similar to the operation actions when playing game. WAF and target survey represent the environment of the game, giving the agent feedbacks. Tell it whether the data packet is bypassed or not, and successfully execute or not. The agent chooses the next mutation actions based on the feedback and the current state. In this way, we model the offense-defense confrontation problem as a reinforcement learning problem. In our scheme, in addition to setting up the environment and designing the reinforcement learning algorithm, we also need to construct the atomic bypass action library and the original malicious payload library. The atomic bypass action library is similar to the basic operation we do when playing games. Here we collect the bypass techniques commonly used by experts and split them into atomic level actions. The original malicious payload library is a collection of payloads commonly used by security experts in attacks. These payloads are usually blocked by WAF. The goal of our project is to use the original payload in this library to bypass a WAF and correctly execute on the target through a combination of bypass actions. This whole process is automatically performed by the trained reinforcement learning agent with very few attempts. In order to reduce the number of attack attempts in actual combat, we divide the environment of the entire solution into two parts: training and actual combat scenario, including external confrontation and internal confrontation. First, we deploy WAFs and volunteer environments of various vendors in the training environment. We train reinforcement learning agents in the training environment to learn how to bypass WAFs of various vendors. In the actual combat scenario, we integrate the trained agent into the automation tools or develop a set of tools by ourselves. In its workflow, the tools will first judge the target WAF manufacturer and then automatically select the agent model according to the manufacturer. Then mutate the payload used by tools, achieve the purpose of the penetration testing the target website. Through the splitting of the two environments, one hit knockout effect can be achieved in actual combat. In order to solve the second problem, that is, to maintain the semantic of payloads and improve the execution success of the mutated payload, we propose a mutation method based on grammar and lexical analysis. The workflow is that first the payload is parsed into a lexical token sequence and a syntax tree. Then mutations are performed on the token sequence and the syntax tree to maintain the semantic environments of the payload. On the other hand, in the reward design, we not only consider whether WAF can be passed or not, but also consider whether the payload can execute correctly or not. Only these samples that can both bypass the WAF and execute the attack correctly can get the maximum reward. We improve the semantic environments of the mutated payload through the two improvements of the sample generation phase and the feedback rewards phase, thereby increasing the success rate of the attack. Then I will introduce the core algorithm in our scheme. The reinforcement learning algorithm we use is the PPO algorithm proposed by OpenAI in 2017. The PPO algorithm is a policy gradient algorithm. The policy gradient algorithm is very sensitive to the step size, but it's difficult to choose a suitable step size. If the difference between the new and the old policy changes during the training process is too large, it is not conducive to learning. If you propose a new objective function that can update small batches in multiple training steps, which solves the problem that the step size in the policy gradient algorithm is difficult to determine. In fact, TRPO is also to solve this issue, but compared with the TRPO algorithm, PPO is easier to solve. The core problem of the policy gradient method is the bias of the data. Because the advantage estimate is not completely accurate and there is a bias, then if the policy update is too far away, the next sampling will be completely divided, causing the policy updated to a completely divided position, thus forming a vicious circle. Therefore, the core idea of TRPO is to make each policy update in a trust region to ensure the multitudes is improvement of the policy. The policy gradient method is on policy, so it is originally required to use the on-policy data for training every time. But obviously, it is too inefficient to throw away the on-policy training once. Therefore, TRPO and PPO are said to be on-policy, but in fact they are off-policy in most cases, and can only be said to be near on-policy. How to do it? That is, the data sampled once is divided into mini batch to train the neural network to iterate multiple times. Generally, we will reuse the data, that is sample reuse. Then due to the use of policy data in training, only the first update is on policy, followed by off policy. The data distribution is different, so we need to use the importance sampling to adjust. The core idea of PPO is very simple. For the ratio, that is the deviation between the current policy and the old policy, do a clip. If the ratio deviation exceeds axima, do a clip. After the clip, the gradient will directly become zero, and the neural network will no longer update the parameters. In this way, in terms of implication, it does matter how many steps are updated, and you don't have to worry about the training being biased. Finally, I will show the experimental results we have achieved so far. First, let's look at the effect of an internal confrontation scenario. We carried out confrontation in two stages. The first stage is black box confrontation, which means that we treat WAF as a black box and only feedback information about whether payloads are blocked or not. In this stage, we generate more than 20,000 bypassable and executable samples, and we extract more than 20 bypass modes from them. We further promote the improvement of our WAF. Second stage is white box configuration. At this time, the program interface inside the WAF will also be open to the enforcement learning agent. In addition to whether blocked or not, the agent will also know what caused the block. In this stage, we found more than 50 bypass modes. In the external confrontation scenario, we fight against several mainstream WAF. We have almost 100% bypass success rate. Our function is integrated into the circle map tools. The effect of one-click injection has been verified in dozens of customers. That's all. Thanks for your listening. I'm sorry that my physical condition is not very good today, so I will cancel the QA session. Here is the QR code of my home page. Please feel free to contact me if you have any questions.